construction.
So, in the last lecture we had looked at dimensional analysis for the heat transfer in a heat exchanger. Okay. Consists of a pipe inside a shell, and there was flow of fluid through the pipe, and the temperature of the wall of the pipe we assumed was some value, okay. And the average temperature in the fluid was at a higher value, and therefore, there was a heat flux from the fluid to the wall of the pipe. So, the dimensional parameters there are of course, the average heat flux, the heat energy per unit area of the pipe, the temperature difference, diameter, length, velocity, density, viscosity and so on. And we had calculated the correlation assuming that there is no interconversion between mechanical and heat energy, okay, in that case. And if we assume there is no difference, there is no interconversion, then we modified the dimensions of the average flux, the thermal conductivity and the specific heat, because these are thermal properties and therefore, they depend upon the thermal energy. And if there is no interconversion, we had defined a separate dimension for that, okay, that heat energy. And based upon that, we had got one dependent dimensionless group, the Nusselt number, which was obtained by dividing the average heat flux by a term that has the same dimension as the right side of Fourier's law of heat conduction. And there were dependent dimensionless groups, okay, the ratio of lengths, the Reynolds number, ratio of inertial and viscous effects, and the Prandtl number. Okay. I had also expressed the another dimensionless group, the Peclet number, as the product of the Reynolds number and the Prandtl number. Okay. So, it is V, the velocity times the diameter divided by something. Okay. That something is this K by rho Cp here. Okay. And just from dimensional analysis, this has to have dimensions of length square per time, the same dimensions as the mass diffusion coefficient. Okay. And therefore, we considered this, interpreted this as the ratio of convection and thermal diffusion. Okay. And we said that when this number is small, there is no the fluid flow does not have any effect on the heat transfer rate, and therefore, the Nusselt number has to be a constant. Okay. On the other hand, if it is large, even though convection is dominant compared to diffusion, ultimately heat transfer from the surface has to take place due to thermal conductivity, okay, because there is no flow perpendicular to the surface, and therefore, at high Peclet number, the Nusselt number does in fact depend upon the Peclet number. Okay. So, those are the conclusions that we drew. Okay. Both for a particle, the only difference is in the particle you do not have the ratio of lengths, the diameter and the length, as you had in the case of a heat exchanger. There was only one characteristic dimension for a particle. Now, this can be used to solve some simple problems, okay, just by a simple analogy. Okay. For example, if I had a particle, okay, of diameter 1 millimeter, which was drying in stagnant air, okay, so that there was no fluid velocity and there was no convective transport. Okay. And let us say that it took about not drying, but cooling in stagnant air. Okay. And the temperature of the particle is initially 40 degrees centigrade, and the temperature of the fluid which is 0 degrees centigrade. Okay. And let us say that the particle takes 60 seconds to cool from 40 degrees centigrade to 10 degrees centigrade. Okay. If I had a particle which was larger, which has a diameter of 2 millimeters instead of 1 millimeter, and all other parameters are the same, how long will this take to cool to 10 degrees centigrade from 40 degrees centigrade? Okay. Now, the time taken for cooling, okay, there is no convection, therefore, it can only depend upon the thermal properties and the temperature difference. Okay. The time for cooling can only be a function of delta T and the thermal properties, okay, rho Cp and the thermal conductivity, okay, and of course the diameter. Okay. And in this case you are keeping the ambient temperature, the initial temperature and the final temperature the same. Okay. So, the ratio of temperatures is the same in this case, okay. Okay, since you are keeping these initial, final and the ambient temperature the same. Okay. The time required for cooling can depend only upon the thermal properties. Density is included in the thermal properties because the energy per unit volume is rho Cp, okay, times T. Okay. So, therefore, the density has to be included whenever the specific heat is included as a thermal parameter. Okay. So, we need to get a quantity with dimension of time, okay, from these parameters, okay. And we just found out that this combination, okay, this combination rho Cp by k has dimensions of length square per time, okay. The rho Cp by k has dimensions of length square per time, okay. So, if I take k by rho Cp, okay, this will have dimensions of time by length square and multiplied by the square of the diameter d square, I will get something that has dimension of time, okay, because rho Cp by k we know has dimensions of length square per time. So, if I take k by rho Cp and multiply it by d square, I will have something, I will get something that has dimensions of time. Okay. So, therefore, the time required for cooling just from this simple dimensional analysis is proportional to d square. Okay. So, if I double the particle diameter, the time for cooling goes up by a factor of 4. Okay. That we could get just on the basis of simple dimensional analysis. Okay. So, this is an example where you can use simple dimensional analysis, do the experiment for a model system and then use dimensional analysis to actually get the value of the time required for a real system. Okay. Because we know that just from dimensional analysis, if the Peclet number is small, then convection is no longer important. The time required for cooling can depend only upon the thermal properties, the density, specific heat, conductivity and the diameter. Okay. So, this is an example, a simple example. Okay. So, let us go to the next problem of momentum transfer. Okay. Flow in a pipe. Okay. Flow in a pipe of diameter d, length L, okay, with average velocity v. We have some velocity profile here. VAV is the average velocity, okay, of the flow in the pipe. Okay. We want to know what is the pressure difference that has to be applied across the ends of the pipe, okay, in order to get the average velocity VAV. Okay. So, that is the problem. Now, if the length of the pipe is much larger than the diameter of the pipe, right, if the length of the pipe is much larger than the diameter of the pipe, okay, in most of the pipe you can assume that the velocity is not changing as a function of downstream distance. Okay. Over most of the pipe you can assume that the velocity is not changing as a function of downstream distance. That is, that the velocity has reached a fully developed velocity profile. Okay. Of course, that will not be true very close to the entrance of the pipe, where the flow comes from some other, okay, from some other equipment, and therefore, it may have some velocity profile that is different, okay, from the velocity profile in the length of the pipe. But provided the length of the pipe is much larger than what is called the development length, the length required for the flow to reach its fully developed, okay, profile. Okay. So long as it is the length of the pipe is much larger than the development length, okay, you can assume that the velocity profile is unchanged with downstream distance in the pipe. And if the velocity profile is unchanged with downstream distance in the pipe, then the stress exerted on the wall, okay, the stress exerted on the wall is basically depends upon, from Newton's law of viscosity, the variation in the velocity close to the surface. Okay. So, if the profile is unchanged, then the wall stress is also unchanged, okay, and this wall stress is equal to what is called the wall shear stress. Okay. The force per unit area exerted by the fluid on the wall of the pipe. Okay. The force per unit area exerted by the fluid on the wall of the pipe, okay, is in the plus, okay, is along the flow direction. Okay. The fluid exerts a force along the flow direction on the pipe, and from Newton's third law, the pipe exerts an equal and opposite force, okay, on the fluid. Okay. The pipe exerts a force in the negative flow direction on the fluid, okay, and the pressure difference is required in order to balance, okay, the difference in pressure between along the flow direction between the entrance and the exit basically balances the stress that is exerted by the pipe, okay, balances the stress that is exerted by the pipe on the fluid. Okay. Therefore, this wall shear stress is related to the difference in pressure just by momentum balance. Okay. The wall shear stress is related to the pressure difference by momentum balance. And if we assume that the length of the pipe is much larger than the development length, so that the wall shear stress is a constant, okay, for most of the pipe, okay, then we know that the total force that is exerted by the pipe, okay, in the negative x direction on the fluid has to be equal to the wall shear stress times the surface area of the pipe. Okay. The surface area of the pipe is pi d times L. The surface area of the pipe is pi d times L, where d is the diameter and L is the length. Okay. L is the length and d is the diameter. Cylindrical surface area is equal to pi d times L. Okay. That is the force that is exerted on the fluid in the opposite to the flow direction by the pipe. Okay. This has got to be equal to the difference in pressure between the entrance and the exit. Okay. The difference in pressure between the entrance and exit times the cross sectional area. Force exerted is pressure times an area. Pressure is exerted along the flow direction, and therefore, the area that is perpendicular to this flow direction on which the pressure is exerted is the cross sectional area. Okay. So, this has to be equal to the pressure difference with a negative sign, because the pressure at the exit of the at the entrance of the pipe is higher than the pressure at the exit. So, the force exerted is pressure at the exit minus the entrance times the cross sectional area, which is pi d square by 4. So, this is the relationship if we assume that the wall shear stress is a constant, because the flow is fully developed. Okay. And this directly gives us a relationship between the pressure difference and the wall shear stress. Okay. Rather, it gives us a relationship between what is called the pressure gradient, the pressure difference per unit length of the pipe, the pressure difference that has to be applied per unit length of the pipe, and the wall shear stress. Okay. The wall shear stress is 4 times the wall, the pressure gradient has to be equal to 4 times the wall shear stress divided by time. Okay. So, this gives a relation between the pressure gradient and the wall shear stress. This tells us an important conclusion can be drawn from this, that if the wall shear stress is a constant, so that the length is much larger than the development length of the pipe, then the pressure difference required for a given flow rate has to be directly proportional to the length. Okay. The pressure difference has to be directly proportional to the length. Therefore, correlations are written not for the pressure difference itself, but rather the ratio of the pressure difference and the length of the pipe. Okay. So, this is the quantity that will be used for writing correlations. Okay. So, either you write it in terms of the pressure difference per unit length or in terms of the wall shear stress. Okay. Either of these can be used for writing the correlation, okay, because the two are simply related. Okay. So, I can write the dependent quantity, okay, quantity is this. Tau w is the dependent quantity. Okay, it has dimensions of stress, force per unit area. Okay, the stress is the force per unit area. Okay, mass L inverse t power minus 2. Okay, force is mass times acceleration ml t power minus 2, and stress is force per unit area. Okay, so there is a dependent quantity. Okay, and the independent quantities are the fluid velocity, the average fluid velocity VAV, the density rho, the viscosity mu. Okay. Velocity has dimensions L T inverse, density m L power minus 3, viscosity m L inverse T inverse. Okay, we have seen these repeatedly. Okay. Therefore, the independent dimensionless quantity has to be obtained by scaling the independent dimensionless quantity combination of there should be one additional thing, that is the diameter d with dimension L. Okay. Note that if we write an expression for either the wall shear stress or the pressure difference per unit length, those two will be independent of the total length. Okay. So, in that case, because we are assuming that the flow is fully developed, we do not have the total pipe length entering the correlation, because we are defining the correlation in terms of the wall shear stress, which is a constant independent of length for a given velocity, provided the length is much longer than the development length. Alternatively, you can use this relation to write it in terms of the pressure difference per unit length. Okay. So, the independent dimensionless group that we get is quite easy. Okay. From these we know that the independent dimensionless group is the Reynolds number. Okay. That is the independent dimensionless group. The dependent dimensionless group has to contain the wall shear stress and some other parameters. Okay. If we had defined it the same way that we had defined the dependent dimensionless group for mass and heat transfer, we would have used the same we would have used Newton's law, which relates the stress and the viscosity and the velocity and the separation, and scaled the wall shear stress by a quantity that has the same dimension as the right side of Newton's law. That is not how it is conventionally done. Okay. If we use the right side of Newton's law to scale the wall shear stress, then we would be scaling it by the viscous scale. Okay. What is conventionally done is to scale this by the inertial scale. Okay. The shear stress is a force per unit area. Okay. Force per unit area has the same dimension as energy per unit volume. Okay. Because energy is force times length, volume is area times length. Okay. So, the wall shear stress or the shear stress has the same dimension as an energy per unit volume. Okay. So, therefore, what is conventionally done is to scale the wall shear stress by a kinetic energy per unit volume. Okay. Kinetic energy is half m v square, kinetic energy per unit volume is half rho v square. Okay. And it is on this basis that we define the scaled wall shear stress, which is what is called the friction factor. Okay. And I can use this expression for the relationship between the wall shear stress and the pressure difference to also write this expression as the pressure gradient, the negative sign, pressure difference per unit length. Okay. And you can easily see that if I substitute for tau w as d by 4, right, if I substitute tau w is equal to d by 4 into delta p by L, okay, I will get here 2 rho V average square by d. Okay. That is just rewriting the friction factor using this momentum balance condition. Okay. That is just rewriting the friction factor using this momentum balance condition. Okay. So, therefore, the friction factor is equal to minus delta P by L by 2 rho VAV square by d. That is the dependent dimensionless group, and the Reynolds number is the independent dimensionless group. Okay. Important point to note here. Okay. This is what is called the fanning friction factor. This is what is called the fanning friction factor. Okay. This definition. Okay. This definition is what is called the fanning friction factor. Okay. There is another friction factor, okay, which is just 4 times this. Okay. It is called the Darcy. Okay. Friction factor is defined as minus delta P by L by half rho Vf square by d. Okay. This is just another convention of defining the friction factor. Okay. The two are equivalent to within a constant. Okay. The two are equivalent to within a constant value. Okay. So, this will, so basically the Darcy friction factor will be equal to 4 times the fanning friction factor. Okay. The Darcy friction factor will be equal to 4 times the fanning friction factor. Okay. So, if you multiply this, the fanning friction factor by 4, right, you will get a factor of half in the denominator. Okay. This is just to alert you that there are 2 definitions of the friction factor, and you have to be careful which definition you use when you actually do a design. Okay. In this course, we will use the fanning friction factor as the definition of the friction factor, but please note that there is another definition, the Darcy friction factor as well, and in order to convert between these two, there is a factor of 4. Okay. That is the only difference. Okay. We will define the friction factor as the wall shear stress divided by the kinetic energy per unit volume for our purposes, okay, throughout this course. Okay. So, in this case we have defined the friction factor as a scaled wall shear stress scaled by inertial effects. Okay. In the limit as Reynolds number becomes small, okay, Reynolds number, recall, is the ratio of inertia and viscosity. Okay. When the Reynolds number is small, inertial effects are not significant, viscous effects are dominant, the wall shear stress cannot depend upon the density of the fluid, it has to depend only on the viscosity. Okay. So, therefore, the ratio of the wall shear stress and the viscous stress has to be the same, it has to be equal to a constant. Okay. The ratio of the wall shear stress and the viscous stress has to be a constant. Okay. In the limit of low Reynolds number. Okay. Inertia cannot be important. Therefore, the only mass dependent parameter you have to scale the wall shear stress is the viscosity. Okay. And you can define a dimensionless group as the wall shear stress divided by a quantity which has the same dimension as the right side of Newton's law of viscosity. Okay. A quantity which has the same dimension as the right side of Newton's law of viscosity. Okay. This has to be equal to a constant. Okay. In the limit of low Reynolds number, the wall shear stress can be scaled only by the viscosity, and therefore, the ratio of the wall shear stress and a quantity which has the same dimension as the right side of Newton's law of viscosity. Viscosity times velocity difference divided by distance, that has to be a constant. Okay. Which means that the wall shear stress has got to be equal to constant into mu VAV by d, okay. And therefore, the friction factor, which is tau w by half rho VAV square, okay. The friction factor, which is scaled by the inertial scale, has to be equal to a constant into mu VAV by d into 1 by half rho VAV square. Okay. And you can easily multiply this and see this will be equal to a constant into 2 mu by rho VAVD, okay, a constant into 2 mu by rho VAVD, okay, which is equal to some constant, okay, into 2 by RE. Okay. So, basically the friction factor in the limit of low Reynolds number has to be proportional to 1 over RE, because the wall shear stress can depend only on viscosity. Okay. We had scaled the wall shear stress by inertial scales. When you do that and the wall shear stress depends only on viscosity, it does not depend upon inertia, then the friction factor in the limit of low Reynolds number has to depend only upon the in the limit of low Reynolds number has to be proportional to 1 over Reynolds number. Okay, that is just a dimensional requirement. Just as in the case of mass and heat transfer, the Nusselt number and the Sherwood number were constants. In this case, the friction factor, because it is scaled by inertial scales, has to be proportional to 1 over the Reynolds number in the limit of low Reynolds number. In the limit of high Reynolds number, we will come back and examine how the friction factor varies on the Reynolds number a little later. It turns out that it depends on Reynolds number even in the limit of high Reynolds number. Okay. That is because transport close to the surface has to take place due to diffusion. Okay. We will come back and examine that in the a little later when we go through an analysis of fluid flows in a pipe, on a flat plate, and so on. Okay. So, those things we will continue in the next lecture. Okay. Next time I will start giving you a physical interpretation of what these dimensionless groups mean. Okay. And on that basis, we will then classify the dimensionless groups and then give you a deeper insight on why the correlations turn out the way that they do. Okay. These correlations that we derived on dimensional analysis basis, why they turn out to be the way that they do, that we will examine in the next lecture. I will see you then.